All right, so continuing on. So this whole time we've been dealing with the standard normal, okay? We've been talking about the standard normal distribution. And the standard normal distribution has a mean of 0 and standard deviation of 1. Okay? And basically all normal distributions are defined by two values, the mean and the standard deviation.
Can we write stuff on our tables or no?
So you'll need to bring these to class next week, okay, for the thing. And so I just ask that you don't write too much stuff on your thing, okay? If you write too much, then I'm gonna have to take this away and just give you a blank one, okay? Sorry, this is standard. My pen's acting up a little. Oh, standard deviation. Standard deviation equal to 1. So all normal distributions are defined by a mean and a standard deviation. Okay. And so, and again, remember these are theoretical shapes that kind of tell us how the values should be distributed, okay? But we can, no matter what our normal distribution looks like, we can convert them back into standard normal distributions, okay? And that's through the use of z-scores, okay? So no matter what the normal distribution looks like, we can quote-unquote convert our values back to the standard normal through the use of z-scores. Okay. Do you guys remember what a z-score was? Okay, what is a z-score? So it's our distance, the distance from the mean expressed in standard deviations. Or in other words, how many standard deviations we are from the mean, okay? Okay, so let's take that, and so we can say, yes, question.
Can you break the formula for z-score?
Sure. Okay, so what you guys learned, so earlier we said the z-score would be x minus x bar over s, okay? Now, when you deal with theoretical things, we replace x bar and s with Greek letters, okay? But, so essentially, it's also going to be x minus mu divided by sigma. These essentially say the exact same things, okay? So x bar is the sample mean, and s is the sample standard deviation. And then over here, mu is the population mean. And sigma is the population standard deviation. Okay. In both cases, you are taking x, subtracting the mean, and dividing that distance by the standard deviation. What does what word say?
The one right above when you started doing the abilities. So keep going left, up, over.
Earlier?
Okay, that's good.
Yeah. This is just from like earlier in the course.
Oh, got it.
Okay. So, I mean, we're finding z-scores the same way. Subtract off the mean to get the distance. You're going to divide that distance by the size of the standard deviation. Okay? It's just symbols change. The idea is exactly the same. All right, is this okay? All right, and so we could say something like in the US, okay, adult females have heights that follow the normal distribution. Okay, and we will say the mean height is we'll say 5 foot 4.5 inches. Okay, and that corresponds to 64.5 inches. We'll say that's the average height of all adult women in the US. These are just approximate numbers, okay? And then we'll say the standard deviation is 3 inches. Okay, and again, this is approximate. Okay. And so we have a shorthand way, okay? So we can say heights come from a normal distribution, 64.5 comma 3. This is kind of a shorthand way of saying all of this stuff, okay? Because we said heights follow the normal distribution. The mean height is 64.5 inches. And the standard deviation is 3 inches, okay? For our international friends who are not familiar with our silly American unit system, 64.5 is, what is it, 2.54? And this is not helpful. Is 163.83 centimeters. And then 3 inches is about 7.5 centimeters. So we'll say about 164 centimeters and 107.5 centimeters, something like that. Okay? Yes, question.
So the symbol, capital uppercase N is
Normal distribution. Yes, yes. Okay? And this little squiggle means the heights come from the normal distribution, where the mean is 64.5 and the standard deviation is 3. Okay? So this is a shorthand way of saying the same thing. Okay? So this is right, because it can get tiresome to continually have to write all of this out. So we might just say heights this. Okay?
The midterm, is it going to be written out or in this short form?
I guess be prepared for either. Okay. Okay, and so when we draw our picture, we get something that looks like this. And we would put 64.5 right there. Okay, is that okay? And then so we can ask a question like, what percentage of women, or what proportion of women have heights shorter than, we'll say, 5'7". Okay, so 5'7" would be 67 inches. Okay, and 67 inches for our metric friends is about 170 centimeters, okay? So what proportion of women have heights shorter than 67 inches? Okay, so when I draw this diagram, I put the mean, 64.5, in the center, right? And then I'm going to draw a cutoff line above 64.5 at 67. And it's asking what proportion of women have heights shorter than 67 inches. So when I shade in my area, do I shade to the left or to the right? I'm shading to the left, right? Okay, shading to the left. Is that correct? So I'm shading to the left, and I want to know what is this proportion. Okay, so I can't go to the standard normal table and look up 67, but I can turn 67 into a z-score and then look that up in the normal table. Okay, so we're going to turn 67 into a z-score. So what is the z-score for 67? So we're going to take 67 and turn that into a z-score. Okay, so what do? I do z is equal to, you know, it's x minus mu divided by sigma, right? So what is my x in this case? 67. What's my mean? Or 64.5. And what's my sigma? 3. Okay. So what do I get? I get 64.5 minus 67 divided by 3. All right, and I get a z. Oops. I'm sorry, I did that backwards. Z is positive 0.833. Sorry, 67 minus 64.5 divided by 3. Okay, so I get 0.833333. I'm going to have to round off to 2 decimal places, so I round off to 0.83. I get Z is equal to 0.83. Is that okay? All right, and then I'm going to look this up in the table. I go to the row 0.8, the column 0.03, and what do we have? We have 0.7967. Okay, is that my answer? Do I have to do anything to that, or do I just leave that?
Leave it.
I just leave that. Okay, so what proportion of women have heights shorter than 67 inches? Our answer is about 79.67%, almost 80%, okay? So the answer here is 0.7967 if we're gonna go off of the Z table, which is, you know, pretty close to around 80%. What? The 3? So why is this a 3? So here I said the mean height is 64.5 and the standard deviation is 3. Yeah, okay. So, or in shorthand we have 64.5 and 3 right there. Is that okay with everybody? Why? I just made it up. I just said, well, I mean, I didn't make it up, but it's like part of the problem setup was heights of US females follow the normal distribution, and the mean is 64.5 and the standard deviation is 3. Don't ask me how I know that, but we're just saying, let's pretend that it is. Okay? And because I've given you that information, now we can answer these problems. All right? Okay, so let's try something else out. Okay, so we will say, I don't know, the, what's a big animal?
Tiger.
tigers. Okay. How big's your average tiger? Let's say
750 pounds.
700 is it really? Weight of an average Bengal tiger.
540.
Okay, all right. So, well, it's quite different if you are a male Bengal tiger or a female Bengal tiger. The average weight for males is 490 pounds. Okay, so we'll say, and I'm making this up. I don't know if this is actually true. We'll say the weight of male Bengal tigers follow a normal distribution. Okay, we'll say the mean is 490 pounds. And the, I'm completely making this up, but we're going to say the standard deviation is 51 pounds. That's probably too much, but whatever. All right. Okay. So now I'm going to ask what proportion of tigers, of we'll say male Bengal tigers, weigh more than 420 pounds. Okay, so what proportion of male Bengal tigers weigh more than 420 pounds? Okay, so I always think it's helpful to draw a little picture. And I'll let you guys do the work here. So what number should go in the middle? 490. Where am I drawing my cutoff? 420, which is lower than 490, right? And it says, what proportion of male Bengal tigers weigh more? So I want the area to the right. Okay, so go ahead and try to solve this. I'll give you guys a minute. I'm going to pause the video if you're watching on YouTube. So please, please use this as an exercise to try this out. All right, so backing up, I'm going to just repeat myself for the YouTube video. Okay, so we first want to turn 420 into a z-score. And so for our z-score is going to be x minus mu divided by sigma. And I do think that's helpful because that will help students avoid problems where they mix up the 490 and the 420, okay? And so we put 420 minus 490 divided by 51. If you got these mixed up, you would have gotten the, you might have done 490 minus 420. We don't want to do that. So we want to do 420 minus 490, okay? We get negative 70, and we're going to divide that by 51, and I get negative 1.37. So I get z is equal to negative 1.37, okay? And then students were asking, you know, what do I do now, okay? So we have a z-score, and what we're going to do is we're going to look up the z-score in the table, okay? So we look up the z-score in the table. We go to, I hope you're all right. We look up negative 1.37 in the table. So we go to the column 0.07, and we have 0.0853, okay? But remember, the table always gives us the area to the left, okay? So that says this part is 0.0853. We don't want this part to the left. We want the part to the right, because it says we want the area that says more than 420 pounds, okay? So we're going to do 1 minus 0.0853. That's right, okay. So we get 0.9147. Okay? So what proportion of Bengal tigers weigh more than 420 pounds? About 91.5%, okay? So about, you know, 91, 91.47%, you know, we could round that off to like 91.5% or something like that. Okay, is that feeling okay? All right, and so I do think it's helpful to, you know, make a little diagram, so just to kind of keep us, like if you get an answer that's like 8%, right? Something like 8.5%. When you look at the picture, you go, wait, that doesn't make sense, because it's definitely over half of the area, right? So there's a little bit of a sanity check that just says, hey, I'm getting 8%. Does it make sense that, you know, only 8% of the tigers? When I look at my picture, it kind of brings you back. All right, is that okay? All right. We might have what we call the reverse question, okay? And so here we might talk about percentiles, okay? And so a percentile, and you might encounter percentiles at the doctor's office, you know, especially if you're kids, if you have kids and you take them to the doctor's office, they'll say like, oh, your child weighs, his or her weight is in the 10th percentile, which means they're on the light side, okay? Or they might say your child's height is in the 95th percentile, which means your child is very tall compared to other people, okay? Or, you know, maybe you've taken a standardized test like the SAT, and then you get your score back and it says your score's in the 80th percentile or something like that, okay? So what a percentile says is that it tells you what percentage of the data falls below that value, okay? So okay, so, you know, for example, if a person's height is in the 73rd percentile, okay, that means 73% of people have heights lower than this person's height. Okay, or, you know, if a dog is in the, you know, 5th percentile for weight, okay, that means only 5% of dogs weigh less than this one. Okay. This concept of percentiles makes sense to everybody? Okay, so let's just try like a very basic question, and so some of you this answer will be very obvious, and so don't shout out your answer, okay? We're gonna let people think about the answer here. Okay, so let's say for again U.S. adult women, the heights follow a normal distribution with mean 64.5, standard deviation 3, okay? And I'm going to ask a question, and again, don't shout out your answer. What is the height of a woman who is in the 50th percentile? Okay, so just think about think about the answer to that. What is the height of a woman in the 50th percentile? Based on the information I've provided. Again, don't shout it out. Think about it. Does this question make sense? The question makes sense, but do we have any idea how to get it, or does it feel like this is mystery magic? Okay. Well, let's draw a little picture here. Okay, so the 50th percentile means I'm going to draw a cutoff, and the area shaded to the left is 50%, right? Does that make sense? So where would I draw a cutoff so that the area is exactly 50%? Right in the middle here, okay? So here, if I draw a little cutoff there and I shade the area to the, whoops, that is the opposite of what I wanted. How does this not? Okay. So this says the area over here is 50%, okay? So then where did I draw my cutoff here? Okay, and what height is that? 64.5. Okay, so what is the height of a woman who's in the 50th percentile? 64.5. Yeah? So far so good? Okay, let's take this exact same thing, okay? And let's make it a little bit harder. So we'll say heights, again, come from the normal distribution with a mean of 64.5 and a standard deviation of 3. And now we're going to ask, what is the height of a woman in the, we'll say 90th percentile? 90th percentile for heights, okay? So does this mean this woman is taller than average or shorter than average? Taller than average, right? So we know that our answer has to be over 64.5. So it's always good to just kind of have a little bit of a sanity check type talk to yourself and just say, okay, this woman has to be taller than average. So that if your answer comes out shorter than 64.5, you know something went wrong, okay? All right, so let's draw our picture here. Okay, so here's our normal distribution. In the middle, I would put 64.5. Yeah. Okay, and what I want to do is I want to I'm gonna draw a cutoff here, and I want the area over here to be what? 90%. So this is 90%, okay? And so now I want to know what is the height that corresponds here. What is this height? Okay? Well, the way we're going to do this is we're first going to find the z-score that goes here, and then we're going to go from the z-score back to a height. So what is the z-score I should use? So first we're going to find what is the z-score that goes with an area of 90%. Okay? And then once we get that answer, we'll convert the z-score back to a height. Okay? So maybe I'll give you guys a second to look up. And don't shout this out. I want to give other students an opportunity to find this z-score. But see if you can find the z-score that corresponds to the 90th percentile, or an area of 0.9. Okay. So take a minute there. Okay. So all you have to do is look in the z table, or your table 2. Okay, do we have an answer for z? What do we have?
-21.2.
I didn't get that. I'm getting z is equal to 1.28 for here. Z is equal to 1.28. I think if I look this up in the table, I think at 1.28 I have 0.8997, which is the closest I can get to 90%, and that's 1.208. So this is the closest value to 0.9. Okay, so I'm getting closest value to 0.9 is 0.8997, and that's z is equal to 1.28. Is that all right? Okay, and so now that I have my z-score, I'm going to convert this from a z-score back into a height, or my x value, okay? And so I have everything except for the x. So I'm going to plug in 1.28 for z. I'm going to leave x, the unknown. Mu I have, and that's 64.5. And sigma I have, and that's 3. Okay, so this is just a matter of algebra, right? Solving for x. What do? We're going to multiply both sides by 3. Okay. And then so I got 3 times 1.28 is equal to x minus 64.5. So now I add 64.5 to both sides, and I have 64.5 plus 3 times 1.28 is equal to x. So that gives me x is equal to, I don't know what that is, 64.5 plus 3 times 1.28, 68.34. Okay, so what is the height of a woman in the 90th percentile? 68.34 inches. So about 5 foot 8.5, a little shy of that. Yes. What did, huh? Oh, because I'm solving for x, right? So I mean, I had 1.28 is equal to x minus 64.5 over 3. So to get rid of the and I'm solving for x. To get rid of the 3, I multiply both. And just yes.
How do you get 1.28? You pulled that off the chart?
Yeah, I pulled that off the chart. So off the chart, I'm looking for the area that's closest to 0.8997. I mean, closest to 0.9, and that's 0.8997. And 0.8997 corresponds to z equal to 1.28. Okay, so it's just this, it's the same process but backwards. Okay, so this time I'm starting with the area, I'm going from the area back to a z-score, and with the z-score I'm going back to a height. Okay, and the other problems, you started with the height, you turned it into a z-score, then you turned it into an area. Okay, so this is the process but backwards. So yeah, the height of a woman in the 90th percentile, you know, about 68.5 inches, 68.3 inches. So it's like 5 foot 8 and something. Okay. Does that sound reasonable? Can we do this? I would like to have more example time, but we're going to run out of time, so I gotta just go on. So make sure you can study this example. You're definitely going to see questions like this on the midterm. Okay. And then there's one more type of problem that we have to cover. All right, for the normal, and then we have the entire other table to cover, but we can do that in the last half hour, no problem. Okay. So heights. Again, we're going to say normal 64.5, standard deviation 3. Okay, and the question now could be, you know, what percentage of women have heights between, we'll say 64 and 67 inches. Okay, so now we're asking for an area in between. Okay, so let me draw this diagram here. So in the center I'm going to put 64. okay? I mean, 64.5. I'm going to put the mean 64.5 right there in the center. 64, I want to know the area between 64 and 67 inches. So 64 is lower than 64.5, so I'm going to draw a line over here at 64, okay? 67 is higher, so it's going to go over here, okay? You know, sometimes you'll get a question like this, and both values are higher than 64.5. That's fine. Both values could be lower. And so this is the way we're going to, what we want is we want this area in between. Okay, that's the area that we want. This is our answer. Our answer is this part. Okay, now the way we're going to get this is we're going to okay, I'm going to draw a little, do some artwork here. Oh, that was not what I wanted. What happened? Okay. Okay, and we'll try this again. Why do you betray me so? Let's try this again. Okay. Can I color this? There we go. Okay. And then try this. Okay. Good. And so to get our answer, we're going to take the orange area. So we're going to say this area is equal to this minus this. So we're going to take, so the green area, green is equal to the orange area minus the blue area. Okay? Can you guys visually see that? Okay? We're just taking everything to the left of 67, and we're going to subtract off everything to the left of 64. And what we will be left with is the area between 64 and 67. Okay? So green is area between 64 and 67. Orange is the area to the left of 67, and blue is the area to the left of 64. Okay? So if we break out this problem into these two smaller problems, we can do this. Is that okay? So do we know how to get the area to the left of 67? Yes, what do we do? What's the steps there? We're going to turn 67 into a z-score, so we get 67 minus 64.5 divided by 3, okay, and we get negative, or 0.83. Okay, and then we turn the z-score into an area, and we get the area to the left is 0.7967. Okay, and then over here, I do the exact same thing. I'm going to turn 64 into a z-score. 64 minus 64.5 divided by 3. Okay, and I get negative 0.17. I'm going to find the area to the left of negative 1.7. Is 0.4352. Okay, so this area is 0.7967. This piece is 0.4352. So this part here has to be 0.7967 minus 0.4352. Okay, so the, did I write that? Oh yeah, 4325, you're right. 4325. I need my eraser. Okay, so we're gonna do that. So we've got the area between which is our green area, is equal to 0.7967 minus 0.4325, and I get 0.3642. If I can do math correctly. What's that? 0.3642, right? So our answer is 36.42%, yeah. All right. Is that good? Feeling okay? All right, well, okay, so let's, now we're going to take out the other table, binomial probabilities, and here we are going to talk about binomial problems. Okay, so we have the binomial distribution. Okay, so the binomial distribution, it's another theoretic probability distribution, okay? And this tells us how many, quote, successes we should have if we do repeated trials of the same thing, okay? So it tells us the probability of a certain number of, quote, successes that if we perform repeated trials of the same thing. Okay, so there are a few conditions. So a few things is basically you're going to perform the same trial n times, okay? So perform the same, these are conditions. Perform the same random trial n times. Okay. Each trial can only have two outcomes. And we've arbitrarily labeled these success and failure. Now, we associate success with good things and failure as with bad things, but these are just arbitrary labels. Probably it would be better to just say yes versus no, okay? So it could be, you know, you're flipping a coin and the coin can either land heads or tails, okay? Now we arbitrarily have to label one side as success and one side of failure, okay? But again, these are just arbitrary labels. And so, you know, it could be whatever we're talking about. We could be talking about picking M&Ms out of the bowl, and we ask, is the M&M blue, okay? Yes or no, okay? We arbitrarily label one of these a success and a failure, okay? You know, or if someone is having a child, we could be, is the child a girl, okay? Yes or no, we have to arbitrarily label one of these a quote success and a quote failure, okay? Which feels rather odd when in certain circumstances, okay? All right, so each trial can only have two outcomes. That's why we call it the binomial distribution. And, you know, with different things, there might be more than two outcomes. If you're going to use the binomial, you have to simplify your world to having only two outcomes, okay? So, you know, with things like with things like gender, life might be more complicated than just having two outcomes, but we have to, if you wanted to apply the binomial distribution, you have to say there's only two outcomes, okay? And that might mean grouping things together or something, but that's just the way the binomial distribution works, okay? So we're going to perform this. Each trial has the probability P for a quote-unquote success. Okay? And we are interested in having X, the X number of successes, of quote-unquote success. And again, the label success might not necessarily be the appropriate label to use, okay? So, a very simple example would be, I'm going to flip a coin 5 times, okay? So I will flip a coin 5 times. And we'll say the probability it lands heads on each flip is 0.5, and I'm going to ask, if I flip the coin 5 times, what's the probability it lands heads 4 times out of 5? Four times. Okay, this is a binomial problem example. All right, and so whenever you have a binomial distribution problem, you have to pick out n, p, and x. All right, so what is, these are the 3 values you need, n, p, and x. So what is my n in this example? Yeah, so what is that number? 5, okay? It's the number. We're going to perform the same random trial n times. We're flipping a coin 5 times, okay? What is p? 0.5. It's the probability of a quote-unquote success with each flip, okay? So the probability of getting heads every time I flip is 0.5 with every flip, okay? And I am interested in getting how many successes? 4. I want to know what's the probability that the coin land heads 4 times. So I have n is 5, p is 0.5, and x is 4. Okay? And so to get our answer, we are going to the binomial probability table. We're going to start off, and then the way we look this up, we look in the order n, x, and then p. Okay? So we're going to start with n is 5. Okay? And then once you get to 5, you're going to go, you see right next to that, you have the column of x's, and those go from 0, 1, 2, 3, 4, 5, right? So we're, within that group, we're going to go to the row that says 4. So we're at n is 5, x is 4. And then we're going to go down to the right, and we're going to find where the column for p is 0.5. You guys see that? Okay, and what is the value we see there? I'm getting 0.156. My answer is 0.156. Is that okay? No? Yes? No? So we got n is 5, and then we go to the row x is 4. So next to 5, we have the column for x, which goes 0, 1, 2, 3, 4, 5, right? Okay. and then within that row that says 4, we go to the column where it says P is 0.5. And we have 0.156. Okay, and so that's our answer. If I flip a coin 5 times, what's the probability it lands heads 4 times out of 5? There's about a 15–16% chance that that will happen. Okay? All right. Let's try this. Okay. So if you guys follow basketball, Chris Paul is out, Blake Griffin's out, Steph Curry's out. It's like all of California has lost their basketball players. Kobe Bryant has retired. What are we gonna do? It's down to you, Clay. And Austin Rivers. All right, so that was a joke. Thanks for laughing. So let's say Chris Paul. He's pretty good at shooting free throws. Let's say we'll round him up. We'll say he's a 90% free throw shooter. Okay. Okay, so we're going to assume every time he takes a shot, it's independent of the other shots. Now that might not be true. Okay, it could be that, like, I don't know, whatever. Okay, but we will assume each shot they don't have anything to do with each other. Okay, and then we'll say in a game, let's say he will shoot 8 free throws. Okay? And so the question is, what is the probability he makes 7 out of 8 shots? Okay, so this is a binomial problem, and we got to figure out n, p, and x. So what do we have? N is 8, p is 0.9, x is 7. Okay, so what's our answer? .383. Okay. Is that what we're getting? Okay. It says actually the most likely outcome, I guess, is him getting all 8 shots in. That's a 43% chance, right? Most probably he makes 8 out of 8 shots. Would be 0.430. And in this case, it'd be n is 8, p is 0.9, and x is 8. Okay, and our answer here, 0.430. Okay. How do we feel about this? It's not too bad, right? Binomial, it's easy. All right, the hardest part with the binomial is not using the table. Okay, usually when you read the problem, you can figure out, oh yeah, n is this, p is this, and x is this. It's usually not too bad. The hardest part is figuring out, like, oh, this is a binomial problem versus this is just a regular old probability problem. Okay, and so the key difference between a binomial and a other type of probability problem is that with binomial, order does not matter. Okay, so one key thing is order does not matter for binomial problems. Okay, So, for example, we could say, all right, DeAndre Jordan is a 40%, or I don't know, is it even worse than that? It's like 40%, right?
Pretty bad.
Yeah, we'll not give him the benefit of the doubt, and we'll say DeAndre Jordan is a 40% free throw shooter.
Are you saying like the order of which the question is written?
Oh, so I'll make a distinction here, okay? So we'll say is a 40% free throw shooter. It's okay. If you guys don't know, he plays center. He's a big guy. He's good at slam dunking, but huh?
I said, still, you're a pro. You shouldn't be shooting 40%.
Yeah, but he's terrible at free throws, and Mark Cuban doesn't like him. So okay. Okay, so let's say, here there are two problems. Okay, so let's say he let's say he takes 4 free throws in 1 quarter. Okay. All right, so we're gonna ask. So one question will be, what is the probability he makes the first 2 shots and misses the last 2 shots? Okay, and then the second question, same setup, will be, what is the probability he makes 2 shots out of 4? Okay. One of these is binomial and one is not. Which one is the binomial problem? The second one, okay? Because in the first one, we are asking for a specific sequence of events, okay? So here we are asking for a specific sequence. And what is that specific sequence? So the specific sequence will be success, success, fail, fail, right? He has to make the first 2 shots and he has to miss the last 2 shots, okay? So this becomes just a regular old probability problem where independent events, and how would I calculate this probability? 0.4 times 0.4 times 0.6 times 0.6, okay? So it's just because all 4 of these things have to happen in this order, right? It has to go hit, hit, miss, miss. Okay, it has to go in that order. All 4 have to happen in that order. So we're going to have like this, and I don't know what this is. This is 0.4 times 0.4 times 0.6 times 0.6. So this exact sequence of events has a probability of 0.0576 of happening. Okay, what's the probability he makes 2 shots out of 4? This one is binomial, and we have n is 4, p is 0.4, and x is 2. Okay, and so what do we get when we look this up? 0.346. So the answer here, the probability, is equal to 0.346. Okay, and the difference between question 1 and question 2 is that question 2 allows for any arrangement of events. We could have success, success, fail, fail. We could also have, I'm going to just kind of list out all of these possible arrangements. Okay, so we have 6 possible arrangements for him to make 2 shots out of 4. Okay, so there's 6 possible ways this could happen, and it's actually no coincidence that this number is 6 times this number. If I multiply 0.0576 times 6, I would get this number. It's just rounded off in the table, but the exact answer is actually 6 times this, and that's because with the binomial, the order doesn't matter. With this question, the order does, okay? And so you have learned how to calculate these things where the order matters, okay? And with the binomial, the order doesn't matter, and the table kind of gives you your answer nice and easily. So you don't have to figure out every possible arrangement, and you don't have to figure out the probabilities of each of these and add them all together, okay? So you know, on the table, on the test, it's not going to say this one is binomial and this one is probability this, okay? You're going to have to just kind of read through the test and figure out for yourself which one's binomial and which one's not, and answer likewise. But again, once you figure out that it's a binomial problem, I think it's relatively straightforward. You just have to identify n, p, and x. You look it up in the table. Question, yes?
Room to work on the,
Yeah, I believe so. Yeah. I mean,
should we bring in paper?
no. So, in my opinion, there's enough room on the table, on the test, to do all of your stuff. You know, if you find that there's not, then I can provide scratch paper for you. But I don't want students bringing their own scratch paper, because then it brings into the possibility for, you know, stuff. Okay, well, good luck. We'll see you guys next week. Please arrive here on time. You'll have, again, the exam will be 2 hours long, so we'll see you.